Okay, so now we would like to review dimensional regularization. And uh, good. So I am going to show it to you with a specific example, okay? So our integral I that I'm going to consider is an integral d4p over 2 pi to the 4. Then we've got I over p naught squared minus p dot p plus m squared plus I epsilon. Now, this integral, I didn't just make it up, it comes from a specific problem. This is the integral you'd need to do if you were calculating this Feynman diagram. So let's allow a momentum k to flow along this leg. We can imagine a momentum p flowing in the loop, and then along this leg we would again have a k. So if I was to drop the two external legs and some constant factors, this is in fact exactly the integral that I am evaluating. So the first step would be exactly what we did before. So we'll do the integral over k naught, okay? So here's the complex k naught plane. And we start off, and this is the contour that we start integrating over. Then we would do exactly what we did before. We would deform the contour into this shape using exactly the arguments that we had before. And then we could again split it into 3 contributions. You can again verify that the contribution from the portion 1 of the contour vanishes, as does the contribution from the portion 3. And then, in fact, what you would be left with is just the integral from portion 2. And that integral from portion 2 takes this form. So we've got minus an integral. Let me write this as d4p Euclidean, just to remind you that we've now landed up in Euclidean space, 2 pi to the 4. And we've got 1 over p Euclidean dot p Euclidean plus m squared. So you could go ahead and do this integral and make sure that you can get this answer. By the way, notice something. In this expression over here, I've dropped the I epsilon. Now, why can I drop the I epsilon? Well, remember what the I epsilon was doing. It was telling me how to deform the poles. And it told me to deform this pole over here to just below the axis and this pole over here to just above the axis. The reason why I needed to know how to deform the poles is that they actually lay on the green contour. But now I'm integrating over the red contour, portion 2 of the red contour. The poles are not on the integration axis at all. And I simply don't need the I epsilon. It's not needed to define the integral anymore. The poles lie well off the contour of integration. Good. So if I asked you to do this integral, I'm sure the first thing that you would suggest is I should move to a radius and angles. So that's what I'm going to do. And okay, so let's do the dimensional regularization step. So here is the dimensional regularization step. So what do? Well, we now claim that our theory is defined in d dimensions. And I'm going to drop the subscript Euclidean, okay? So this will be 2 pi to the d. And then we will have 1 over p squared plus m squared. So everywhere where I had 4 dimensions, I've just plugged it into d dimensions. And now I want to swap to a radius and some angles because I know that the integrand doesn't depend on the angles at all. So I will get the minus sign survives. Then I will have an integral over some angles. This will be an omega d minus 1. And this will be an integral over an s d minus 1 for each value of p, the magnitude of the momentum. Then I've got this integral over p, so this will go from 0 to infinity, dp over 2 pi to the d. And now I need to include the p to the d minus 1. Okay, this, guys, is really not a big deal remember, okay, here's just a little bit of motivation for this. Remember, in 3 dimensions, if you had dx, dy, dz, well, this was a length cubed, and this became sine theta, d phi, d theta. Then we had a dr times by r squared. This stuff, which depended only on the angles, you could call that d omega 2, and it was dimensionless. Now, the only way then that we can get a length cubed is if we include a factor of r squared. Here too, my measure was momentum to the power of d. I've got a dp. I need d minus 1 powers of momentum to get the dimensions right. So that p to the d minus 1, that's its origin. You can understand it just from dimensional analysis, okay? We don't have to bother calculating a full Jacobian. And then let's just fill in the rest of the integral that we're performing. We also have over e squared plus m squared. Okay, good. So we're going to calculate these two integrals in turn. So let's look at this first integral, okay? So I've just outlined it in blue. This is the integral over the unit sphere in d minus 1 dimensions. So how do we do that? Well, there's a little trick with doing integrals. It's always a trick. So we'll have an integral, d dx, and e to the minus x dot x. So first of all, we want to do this integral exactly. So how do we do that? Well, what is this integral? Well, it's an integral dx1, an integral dx2, keeps going up to an integral dxd. All of these, by the way, are from minus infinity up to infinity. Good. And then we've got e to the minus x1 squared minus x2 squared minus x3 squared dot 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 minus xd squared. What is this? This is just an integral from minus infinity to infinity dx of e to the minus x squared raised to the power of d. And you know what this is. Each integral gives you the square root of pi. So this is going to give you the square root of pi raised to the power of d. Good. So that was pretty easy to evaluate directly. But we can also make a change to angles. So this will be a d omega d minus 1. And then an integral dr, r to the d minus 1. Again, this is just the measure factor. d dx is length to the d. If I want to get length to the d here, dr is length, so I need to multiply by r to the d minus 1. And then I've got e to the minus r squared. And this integral over r goes from 0 to infinity. The integral d omega d minus 1 will be over a d minus 1 sphere. Now, look at this r integral. I'm going to make a change of variables. I'm going to say that t is equal to r squared. Then dt will be equal to 2r dr, which means that dr is equal to dt over 2 square root t, okay? So that's the change of variables that I'm making. So then this will become an integral d omega d minus 1 over the d minus 1 sphere. Then here we'll have an integral dt. So let's take the 1 over 2 out. So we'll have 1/2. When r is 0, t is 0. When r is infinity, t is infinity. So there's an integral from 0 to infinity. Then we will have t to the d over 2 minus 1 over 2. But there's also a minus 1 over 2 from the measure. So we'll have a t to the d over 2 minus 1. And then we'll have an e to the minus t. So I just changed variables. It's a very straightforward computation. I'm sure you will not have a problem. But now this is very interesting, you see, because this integral over t is something that we recognize. This integral over t is nothing but the gamma function of d over 2. And the gamma function is a very well-known function. So what we learn from this is that the integral d omega d minus 1 over the sd minus 1 is equal to 2 pi to the d over 2 divided by gamma to the d over 2. Good. And notice, you know, on the right-hand side, I've got pi to some power gamma evaluated at d over 2. I can plug in a complex value of d, no problem whatsoever. Now let's look at this integral sitting over here, okay? So this is the integral that I'd like to do next. I'm going to do a slightly more general integral than that one. So the integral that I'm going to do is the following, okay? So let me just remind you, this is the integral that we want to do. So minus 2 pi to the d over 2 over gamma d over 2. So this is the integral over omega d minus 1. I just plugged in that value. And then the actual integral that we want to do is this one, dp over 2 pi to the d p to the d minus 1 over p squared plus m squared. Okay, so how are we going to do that integral? That is just exactly the value of I here. I just plugged in the value for the first factor. Good. Okay, so the slightly more general result that I'm going to quote and then derive is this one. Im is equal to, so we'll take an integral from 0 to infinity dp, looking pretty similar to the line above. We'll take p to the d minus 1, good. But now we'll take p squared plus delta to the power of m. The reason why I am evaluating the slightly more general result is that, as I said, we're studying a specific Feynman diagram, but for any Feynman diagram that you study, you'll usually get this integral to do with some value of m. And let me tell you what the answer is, and then we'll derive it. This is gamma, the gamma function again, of m minus d over 2. Then we've got gamma of d over 2 divided by 2 to the delta m minus d over 2, and there's a gamma of m. Okay, so let's see how to do this. So let's start off with integral dp, p to the d minus 1 over p squared plus delta to the m, 0 to infinity. So that's the integral that we want to do. First step, make a trivial change of variables. We'll have 1/2 dp squared from 0 to infinity. So we're just changing from p to p squared. Then we'll have p squared to the d over 2 minus 1. Now, the reason why it's minus 1 and not minus 1 over 2 is that there's also a 1 over p that we need to include from the measure. Okay, so do the change of variables carefully. But what I've written here is correct. You might think I've made a mistake. I didn't. Okay, good. So that's the integral that we want to do. And now we're going to change variables. We're going to say x is equal to delta over p squared plus delta. So p squared ran from 0 to infinity. When p squared is 0, x is 1. When p squared is infinity, x is 0. So the integral over x, okay, so this is an aside. This is equal to here. We're going to get an integral dx from 0 to 1, okay? And you should do this whole integral very carefully. Oh, let me move this over a little bit. Good. Okay. Next, if I have this for x, then what is dx equal to? Well, dx will be equal to minus delta over p squared plus delta squared dp squared. That's good. That's the dp squared I want. But this can be written as, so what is this? This is like x squared over delta with a minus and a dp squared. Great. So I know the measure, I know the integrand. It's just a case of plugging it in. And I claim that this is what the answer is. 2 to the delta m minus d. And then we've got the integral dx. We have got 1 minus x raised to the power of d over 2 minus 1. And then we've got x raised to the power of m minus 1 minus d over 2. And this last integral over x we can do by noticing that this is a known integral. If you look at what's called the beta function, so this is, you've got the gamma function in maths, you've also got a beta function. The beta function is usually written as beta of x comma y, and this is equal to, it's an integral from 0 to 1, t to the x minus 1, 1 minus t to the y minus 1 dt. So look at this. It's an integral from 0 to 1 of the integration variable to a power, 1 minus the integration variable to a power. And this is exactly the form of the integral that we've got over here. Okay, so this really is the beta function. And this thing has been evaluated, and the answer is gamma of x times gamma of y over the gamma of x plus y. Okay, so this now is our answer for doing the integral in d dimensions. So how did we do it? When we went to d dimensions, we had to integrate over the angles. So this blue factor, we did that nicely by using Gaussian integrals and the definition of the gamma function. And then we had to do this integral over the momentum, this thing circled in red. And we did that nicely by a change of variables and relating that integral to the beta function. So we know how to do these integrals in principle. Now, you would never actually do these integrals yourself if you were evaluating a Feynman diagram. You'd go and you'd look at tables. So I've given you tables in the notes. Another great place to look for tables of dimensional regularization is in the appendix to the book by Peskin and Schroeder. But I guess many quantum field theory textbooks will have tables of integrals performed using dimensional analysis. Good, we'll continue in a moment.